and helping you understand what you need to know. So I gave specific questions. That's kind of like your homework. I'm not going to collect it or anything, but you could if you want to turn it in as soon as answering those questions. And then what you don't understand, right? You're looking at how you do those type of questions when you're studying for this or the TEAS exams. You go through the questions. What you don't do is say, I don't know the answer, I'm going to look it up. Oh, it's C, I get it. You don't get it until you can answer that. You want to say, okay, here's my gap in understanding. I'm going to go back to the book. I'm going to read about it. I'm going to ask him what I don't understand about. Not what's the answer C, but rather is have an understanding of what they're trying to ask and where your gaps in your knowledge are. Right? That's the best way to study things. Just take tests over and over again. On the learning objective slides, I put at the back, at the end of the chapter, there's the chapter summaries, which give you a little bit of the information, the page number where that information is. And then after, there's review questions, right? Like 1, 2, 3, and then I put some specific ones. The ones that weren't relevant, I skipped, but the other ones, and if you want to do them, do them. If you don't. That's up to you. I'm saying that's a good way to study, right? All right. So, everybody remember this path? Everybody forget everything?
Yes.
It's bad in physiology, right? Anatomy's, in a way, it's easy. You're looking at a single structure, you're describing it. For physiology, things are moving around a lot, right? And we don't want to be able to follow. There's pathways, right? All these pathways here. And there's concepts that come up over and over again, like that last one, right? Change in blood pressure, tack in foot, right? That all, they have commonalities, right? Themes that you should be able to transfer from one to the other. So here, last time we talked mostly about like hormones and stuff binding to some kind of membrane receptor that was causing this pathway activation, G proteins, right? Complicated stuff went on, magic, cyclic AMP, protein kinase, all that stuff. Right? Today, we got that signal molecule right there coming in, and mostly we're going to talk about it activating some kind of ion channel, right? Where stuff is flowing in or out of the cell, right? And that creates ultimately what we're concerned about today is this electrical signal, right? That it's going to create of some sort because the flux of ions in the cell is going to change, right? In the cell electrical components, right? But also, that electrical signal is going to do other things sometimes. It's going to trigger a calcium release. That'll be relevant throughout this whole unit, right? This calcium release because of that electrical signal. But otherwise, right, it's an electrical signal that is going to be the focus of our lectures today, right? So when we talk about those electrical signals, we talk about the going through a neuron today, signals as it passes from one part of the neuron where it starts. Over here, right, you're going to get signals that are going to be coming from the dendrites, right? That's going to be the input. Over there, the dendrites are receiving the signals. That's the part of a neuron. And then the signals are going to travel down. Good. Signals are going to start in various places in the body, and they're going to travel down to a certain area of the axon, right? That initial segment called the trigger zone, right? That's going to sum up the integration center. It's going to be the sum of all signals. And then from there, the output over here is going to be this electrical signal that's actually going to jump all the way down. And then the effect, the target cell will be the next synapse in line, or maybe a muscle cell or something. And the output signal will actually be a neurotransmitter release. Right? But the parts of a neuron over here are what we'll be we'll be looking at today. This, as a signal passes from the dendrites through the cell body, through the trigger zone, through the axon, all the way to the end, right? So all these parts people are more or less familiar with from anatomy, hopefully, right? The parts of the neuron. I'll use these as if you're familiar with them. Dendrites, the cell body, the trigger zone, the axon terminals. And we're going to be kind of looking through as the signal passes through an individual neuron. Tomorrow, we'll be talking about what happens once the next neuron receives that signal and what it does with it, right? How we integrate that information. Okay, and also relevant to today and to tomorrow and the next lecture, right, is the fact that often this electrical signal, well, always the final sort of outcome is that electrical signal might lead to these voltage-gated calcium channels, which are going to be a signal in themselves, right? This will be true for the muscle certainly, but at the end of every synapse, right, they're going to release the calcium input is gonna cause a release exocytosis, right, of the neurotransmitter, right? So this would be another important factor that comes up, right? So, electrical signals, right? There's an electrical signal flowing through the neuron. What exactly are we talking about is what the subject is today, right? The different types of electrical signal flowing through there, right? And just so we're clear, right? When we're talking about an electrical signal going through a wire cable, right? There's all these metal ions and stuff. There's electrons passing through very fast, right? Going through from one end to another, right? Super rapid, right? That's all electron transfer. Right? And then that signal in a neuron, right? There's going to be an electrical signal going down very fast, a wire, a cable down here. But that signal is going to be mediated by sodium, potassium, calcium. Right? That's going to be the electrical signal. Those charged ions, positive or negative ions, are going to be what's going to cause that electrical signal. Okay? So there's going to be ion distribution. The cell membrane, that phospholipid bilayer, acts as an insulator, right? Separating charges like a battery, right? And what we'll see is these channels are going to be the conductors of electricity, right? Ion flow through those channels are going to be what the electricity flow is through, right? And down the cytoplasm right there. So just to be clear, we're talking about electrical signals. It's about sodium, chloride, potassium, calcium moving through these channels. So we talked about this last unit, about the different sort of channels that affect your cell permeability to anything, particular thing, right? The phospholipid bilayer didn't let ions through, but these channels, whether they're open, right, or gated in some way, right, we're going to cause a difference in the permeability. It's going to allow charged ions in or out of the cell right there. Right? Everybody kind of something about that, right? And then those channels could be gated too, right? Certain things could open them or close them right there. And those opening and closing, there's all sorts of different channels with certain different dynamics. We're not really going to get into them too much, but they're going to be open. We'll talk a lot about voltage gated channels today, right? So these are the channels, right, that changes the permeability of a cell, right? This is a very dynamic process, right? So just to walk back a little bit, last time, right, I talked about magic signals and signal transduction from a sensory receptor, right? It was getting signals like the mechanoreceptors in your skin. You touch it and you get a signal, right? In that case, there was an actual physical kind of structure that when you push it or whatever, right, it kind of opens up this gate right here, and then ions flow in, right? Charged ions flow in. It changes the electrical components inside and outside the cell right there, right? So we didn't talk about this. You might have looked at it, right? But mostly we talked about touch receptors in the skin, but all over the body, right? When sound goes in your ear, right? Sound goes in your ear, and that's transmitted through all the tympanic membranes, creating vibrations that goes in here. It causes this pressure wave in this membrane. And that membrane, the way the anatomy is set up, right? These receptor cells have all these mechanical receptors that open up in response to sound. That's how sound turns into electrical signals, because that's going to cause this to activate these sensory receptors, which go in your brain and you interpret sound. Right? That's a mechanoreceptor. Right? That's just from last time. We want to understand this is a change in ion flow that's created right here. That's going to create this signal. Today, when we talk about gated channels, we'll mostly be talking about these voltage gated channels. Right? That is, they're going to respond to a change in electricity, right? And then open up and cause an ion influx or outflux, right? Or maybe that signal, the electrical signal itself, is going to cause a calcium influx. These voltage gated calcium channels, voltage gated sodium channels, voltage gated potassium channels. And then the voltage gated calcium channels will actually cause a exocytosis of the neurotransmitters. The neurotransmitters are the chemical signal that open up these ligand gated channels, right? So these are all the channels we'll be kind of discussing that are going to be very dynamic, right? They determine the cell membrane potential, the difference in between them, and they'll also be, when we talk about electricity flow and changes in them, these are all the channels we're going, right? So all these, there's a couple lists of where, you might find them. They might be more distributed, like leak channels. The open ones are all over the place. Right? Ligand gated channels we're going to find right in the synapse, right? The connection in between them. Mechanically gated channels, usually on receptors and stuff like that. Right? And these voltage gated channels, really the voltage gated channels, when we talk about excitability in the cell, the voltage gated channels are the key point. Voltage gated channels that are gonna open up in response to a voltage change, right? And so this is what, first, we're gonna talk about what these voltage changes are, what all that means. So when you see a picture like this, you can see these positive, these pluses and minuses, right? That indicates there's more negative on the inside of the cell than is on the outside, right? That's the general sort of description of that. And so what we're gonna walk through, oops, right there, we don't need that. What we're gonna walk through is this next step. They're gonna set up a sort of hypothetical situation, right, like this, where we're gonna say a cell, remember, the insulator is the phospholipid bilayer, right? If there's no channels in there, the ions are gonna stay separated, right? And they walk through a sample, right, but kind of think of it really easy, really simple sample right here, right? Let's say there's a box and it's got a high concentration of sodium chloride, which of course are separated because they're ions, right? They're dissolved, they're dissociated in science right there. You got a high concentration on this side, and then you got a lower concentration, that concentration over here, right? Maybe even smaller, but whatever. Right, high concentration, let's say this is 300, let's say this is 200 milliosmoles, whatever. Okay, and they're separated right here. There's a difference in concentration, right? Where would sodium and chloride move if they could? This side to this side, right? They would move. However, this membrane is keeping them apart, right? It's keeping that concentration rate. And that's also, they're electrically neutral over here. The charge is gonna be the same on this side and that side at this point, right? So now we're gonna add like this sodium selective channel. Just sodium, right? Just sodium. We'll put a little channel in here, right? Chlorine can't move. These normally are kind of balanced. They want to stay with each other, but sodium is going to move. Chlorine would like, they both like to move down here. Only sodium can. Yeah.
Okay, so depending on what's going on, so what happens, so the chemical is being sent to the axon terminal, basically, and then that chemical releases, where is the influence does that open up the channels themselves?
It will. That's like 20 slides from now. Right here, we're just talking about how this electrical gradient is set up in the beginning, right? How we have a chart, what makes a cell different on the outside than the inside, basically. We're starting with the very basic stuff, right? So we'll get to that whole part when we're talking about sodium inflow, now the axon, but here we're just talking about the cell, just sitting there, a cell. This is an artificial situation where we separated these components, and now I've added a sodium selective membrane. So only the sodium is going to move in down its concentration gradient. That makes sense, right? Sodium is going to move down its concentration. It's going to move in, but it's a charged ion, so what you end up having is all of a sudden we've gone from a neutral electric boundary right here to a more positive charge right here. Right? On this side it's going to be positive. On this side a negative charge starts to develop. That all makes sense?
Mm-hmm.
Okay. So the sodium is moving down its concentration gradient, but at a certain point it says, wait a second, I feel pull. I feel pull going to the other side. So it's going to stop diffusing down its concentration gradient because it's going to be attracted to the electrical gradient, that negative charge. Everybody knows positive go to negatives, negatives go to positive, right? They're attracted to each other. Chlorine, the reason it stays is because chlorine can't get through here, right? That's why this side is staying negative, whereas we're developing a positive charge over here, okay? That makes sense? So, you know, this ultimately will be the cell membrane, and it won't be sodium that is so permeable, but this is the basic concept that we want to look at right here. And sodium's trying to move down here. It does. It will move until, at a certain point, the negative charge that develops, because of its leaving, is going to pull it back in there. So there's at some point, there's going to be a balance between the concentration and the electrical pull, right? And when they're balancing each other, when there's no more net movement, right, that's when we'll call, that's the ion's so-called equilibrium potential. We'll get back to that, but that's when it stops moving. Okay? Where does it stop moving? Right, it's going down its concentration gradient. We know why that's happening. Normal diffusion properties, concentration differences from 300 to 200. But it stops at a certain point because we develop a negative charge. Each ion that moves over contributes. In fact, from here to here, once there's a negative, sufficient negative a charge developed enough so that it stops moving, this goes from 200, the concentration gradient, even though there's an electrical gradient, it goes to 199. Right? The concentration gradient doesn't really change very much. A few ions are enough to kind of change the electrical thing. Right? That's sort of something that some kind of people that misses, and it's not something I actually tested on, but the concentration gradient really doesn't change. That is, the ion, the electrical pole is so much stronger than the concentration gradient. Right? This is just normal diffusion property. This is actually an electrical force going through there. Right? So the concentration gradient doesn't change even though the electrical gradient changes. So this is what we call an electrochemical kind of gradient. Electrochemical, the chemical is the concentration part, the electrical part is there. Does that make sense? All right, so we'll walk through this again over here. And this is their example in the book, right? They're given a little bit more realistic. This is just like a artificial cell with sodium chloride that you can understand positive and negative charges. So in this case, they're going to do the same example, okay? In this case, they're going to kind of do a similar thing. You have a cell. It's got, they're calling it an equal distribution of negative and positive charges. And that's because the outside, the extracellular fluid, sodium chloride ions out there, electrically neutral. And on the inside, mostly what gives the inside of the cell, you got large proteins and stuff that are overall negative charge, right? And they're going to cause the cell to be a little negative, but you also got a lot of positive potassium ions in there kind of balance. So in this situation, they're saying there's an equal charge between these two, right? There's no electrical difference between them, right? Over here, because the positive potassium, the negative anions, again, which are usually proteins and phosphate molecules and stuff like that, that gives the overall negative charge. And on the outside, you got sodium and chloride. Electrically neutral, in other words. The insulator, again, is a phospholipid bilayer that doesn't allow ions to pass through them. If we want to allow ions to pass through them, we got to put a channel in there, right? So, we look over here. In other words, chemical disequilibrium, there's a difference between the potassium and chloride. And I should write that always, one crucial thing to always remember, always the case in the natural thing. The reason they're using that is that in a cell, you always have a high concentration of potassium. These are the two important players here. On the inside, and a high sodium on the outside. And the chlorine, you know, for the most part, we can kind of ignore right here, but these are the big differences. And sodium always wants to go that way. Sodium always wants to go this way. Potassium always wants to go the other way. Until the charge is big enough, right, that it's going to be pulled back, right, as far as the concentration gradients. So here, right, they're in chemical disequilibrium. That is, there's the differences in charge, but in this case, they're saying, right, the electrical thing is the same. Here, they're going to add instead of adding this sodium selective ion, they're going to add a potassium ion in here, right? So what's potassium going to do?
Down its concentration gradient.
Which is
On the outside.
outside the cell, right? It's going to go outside the cell. So
Through the-
potassium is flowing out. Potassium is a positively charged ion. What happens when positive ions leave the cell? The cell,
It's gonna cause a voltage change.
well, not really here in this case. It's just the voltage change won't happen until we get to those voltage gate channels. Here we're just talking about a leak channel that we put in. Calcium, potassium, the K, is going to flow out through its concentration gradient, and the same thing over here is going to happen. The inside of the cell
I was gonna trap more.
is going to become negative.
Yeah, so it's gonna trap more, I guess.
Well,
Polarity.
so now all of a sudden the cell is negative on the inside because of the potassium leaving, right? So the cell is becoming more negative relative to the outside. All right, it's kind of like you're in a house, you're air conditioned right there, and somebody opens up a window, right? All the hot air flows in. There's a little temperature change around the window right there. You shut it and that stops, right? Same kind of thing. You put a window in for potassium, potassium's going to leave. But at a certain point, now this is where the analogy stops, right? The potassium's leaving, a negative charge develops on the inside, and it only flows out so much. Right? It's only flowing out so much. Right? So at some point, electrical gradient is the opposite direction of the concentration gradient, right? And at some point, it's going to reach so-called equilibrium where it stops with the electrical pole. It is exactly in opposition to the concentration pole. Everybody with me so far? Right, this is what we're talking about. We're setting up basically the resting, so-called resting membrane potential of the cell, why the cell has this so-called potential difference, right? A difference in between the outside and the inside of the cell. Okay. So in this example, potassium has reached where it stops, right? The efflux due to concentration gradient is equal to the pull of the chemical gradient, right? I mean the electrical gradient coming in, right? So they're going to be equally opposed, right? This is where they become equilibrium potential, right? Potassium. All right? Everybody with me so far? This is how we set up the cell membrane potential right here, right? And it's all going to be largely due to potassium in this case, right? Because potassium stays in here, right? Because of these ions, these negative ions that are in here, like big proteins and stuff, makes the charge. Potassium's kind of drawn into some point, but it's going to leave until it reaches a certain point. The actual number is it's going to leave until the cell is negative 90 millivolts. Right? It's going to keep on leaving, then it will be actually in equilibrium. Right? Cell isn't going to be exactly 90, which we'll talk about in a second. But everyone understands the equilibrium potential, where the balance is. Yes.
That's only possible because of the leaky channel for potassium.
It's only possible because the cell is very permeable to potassium. Right?
That's why it has a leaky channel.
That's the leaky channel. There's a lot more potassium, leak channels, right? So sodium, potassium. We're going to start off with this concentration gradient where there's a lot of potassium inside the cell, and it's going to leak out to a certain point, right? To a certain point where it reaches equilibrium. That is where the efflux due to concentration is equal to the influx due to the electrical gradient. Okay? I don't know if the blank faces are yes, if I'm bored, I know it's so easy, or I don't understand anything. Which one is it? Do you totally understand it? Or are you totally confused? A little mix of everything. This is like kind of simplest part. This is the setup, right? How the cell has this difference in positive and negative charges. And we're going to use that like a battery, basically, right? We're going to use it because we're going to see that we're going to create these electrical changes in that membrane potential to send the signal. Okay? So all these living cells over here have what's called a membrane potential. That is the difference between the outside and the inside of the cell. The cell is going to be negative relative to the outside. That's the difference over there, right? The membrane potential difference. And when we say the resting membrane potential, that's the steady state. The resting membrane potential, for all our purposes we're going to talk about, is a minus 70 millivolts. The minus means it's slightly negative. When millivolts is very small, right? There's a small difference between 70, minus 70, difference between the outside. Okay? It's relative to the extracellular fluid. We just set the extracellular fluid at 0. I can say that the inside is more 70 degrees more negative than the outside right here, right? And so that's due overall to the concentration gradient. Mostly we're kind of concerned about potassium right there as far as the resting membrane potential. Right? But the fact that it's negative in the first place, because remember potassium is a positive ion. So why does it set minus 70? Well, there's a lot of negative ions in here. The reason of particular minus 70 is that it's going to flow out to a certain point, right, and create a gradient right there, right? And then there's also going to be sodium channels and stuff like that, chlorine channels, right, that make it this minus 7, right? So the sum total. There's equations and stuff I'm not asking you to learn or anything. This is the general principles, right? Concentration gradient and the permeability, that's what makes that rest from membrane potential, right? The potassium Potassium channels are much more numerous than sodium channels, right? Okay, so if I ask you, what makes up a membrane potential, you'll say the concentration gradients, right? And then you'll say the permeability, right, overall the ions, right? The big player over here is that potassium one, right? That's gonna be maintained, right? Sodium, potassium's leaking out, sodium's leaking in a little bit, and then the actual minus 70, right, fine-tuned by that sodium potassium pump, keeping those concentration gradients the same. Resting membrane, this is when the cell's just sitting there, nothing really's happening, right? Resting membrane potential, right? And that difference, the fact that there's a lot of sodium ions that wanna get in, right, we're gonna use that like a dam, right? Water coming in wants to go through here, and we're gonna use that energy to drive these cell processes right here, right? The excitability of the cell itself, that electrochemical gradient. You with me so far? Okay, so if I asked you, what forces are promoting sodium leak into the cell?
The polarity shift.
Why does sodium want to go in? Is the cell negative? Yes. Are positive charges attracted to negative charges?
Yes.
Yes, so there's an electric pump. Is there more sodium outside than inside? Yeah, so electrochemical gradient, right? Those are the ones that are driving sodium in. Here, potassium, how about that? Is there an electrochemical gradient for both?
No.
So this gets a little more complicated, right? At this point, at minus 70, you don't know this yet, but at minus 70, right, potassium will flow out its concentration gradient. It would keep flowing out when it's minus 70. It would keep on flowing out. Right? When you look at charts like this, right, look at the concentration gradient over here. Right? You look at the 150 versus 5 is the concentration gradient, but it would keep flowing out actually until it reached negative 90, right? That's when it would stop. That's its equilibrium potential. The fact that the cell is minus 70 is due to leak channels and stuff, sodium channels flowing in a little bit, right? So it's not quite, it's very close, in fact, to the potassium equilibrium potential, right? And then when you look at sodium, over there, sodium would keep on flowing in. It would keep on being attracted both through concentration and electric until the cell was positively charged, like plus 30 millivolts, right? So those are those two kind of things. And if you look at, the interesting one is calcium, right? 1 millimolar outside, right? It looks about, a little less than potassium, but if you look at the inside, it's like 110,000 times less on the inside. So calcium concentration highly concentrated outside, even though it's low concentration overall. You don't have to worry about that in particular, but it would keep flowing in quite a bit, right? As long as you let it. All right? Everybody with me so far? Sure. I got one sure. How about this one? What would happen to the resting membrane, that is the normal minus 70 degrees? What would happen if the extracellular potassium concentration increased? And that is, you kind of started abolishing that concentration gradient. And what would happen here so if you abolish the concentration gradient, would that make it less likely or more likely that sodium is going to flow out the cell? We're abolishing the concentration gradient, basically, let's say. There was enough in there. So just, again, I'm not going to make you learn the Nernst equation right here, but the membrane potential, concentration gradient. If this changes, the overall membrane potential is going to change right there because of potassium. Right? And then what happens is you change that whole thing, right, from 150, let's say the extracellular fluid is 100, right, you would definitely decrease it, right? So overall, right, the resting membrane potential would rise, right, become more positive. It becomes more positive because there's less ions. Remember way in the beginning, I told you, this is where you want to definitely draw things out and look at these. Remember I told you in the beginning, think it this way. What are one of the ways, lethal injection, what are they injecting people to kill them? Potassium chloride. So you're flooding the whole cell with potassium. Basically, that's kind of abolishing all these concentration gain for your heart and everything like that, right? And that's going to basically totally destroy the electrochemical gradient over there.
Professor, what is the answer? A?
So the answer, you want to draw it out? 'Cause I don't know,
Yeah.
I have to draw things out, I'm a visual
Me
learner.
too.
Every day I remember, so here, again, high concentration, it's gonna flow to the low, right? That would tend to make the cell, as it flows out, right, a little more negative. But if it wasn't flowing through, right, so the cell is minus 70, then as the cell leaves, it becomes, as these potassium leaves, as potassium leaves, right, the cell is gonna become more and more negative. Now, if you abolish this, and there is no net movement, sodium stays in the cell and the cell becomes more positive, right? The cell inside becomes more positive. So anytime you get a question like this, you just draw it out and you kind of think of it in these big terms. Right? So all these kind of things keep on, these themes come back, you understand high to low and everything like that. Now we have a new concept besides high to low, we got this electrical sort of pole going in the opposite direction. That makes sense? In any case, when we learn about the excitability of heart cells and stuff, right, and this is why the heart is gonna stop actually. You need this potential for all these living processes right here. All right, so now we got the membrane potential down. We know why it's roughly a certain one and why it's stable because of the permeability, the concentration is. Now we're gonna be looking at what happens when you poke it a little bit, right? When you change things a little bit. Changes in the permeability are gonna cause changes in the membrane potential. And it's gonna go above and below the baseline. Here's your resting membrane potential. If you stick a couple of, say, sodium channels, the membrane is going to depolarize. Polarize means a difference. When you depolarize something, it becomes less different. Right, so you're going over here, you're going back to the so-called zero, which would be totally depolarized, right? So it's moving toward positive charge right here when you're depolarizing. This is the word, this is the definition of depolarizing. Over here, if you move it toward a more negative charge, that is, it gets farther away from zero, right, lower than the resting membrane potential, it's going to become more negative. It's called hyperpolarizing. Become more polarized. Okay. Any movement back toward resting membrane potential, whether it's from a depolarized position, going back to minus 70, or something from like minus 90, going back to minus 70, that's called repolarization, right? Either direction. Yeah.
Is it because of the potassium leaky channels that cause the hyperpolarization?
Yes, that will be something that will come up, right, in the end, when we talk about the end of the action potential, the hypersolarization phase. But again, that'll be something we'll kind of step through as we get to it. Right? That is true, right? But these are the terms we'll use, right? And again, repolarization could be from either direction. We're just bringing it back to minus 70, right? From either direction. Does that make sense so far? And so now we're talking about changes, right, in that membrane potential here. So the two types of signals in an individual cell right here that we're going to be talking about are the so-called gradient potentials, right? And you can think of that, you throw a pebble in a pond, there's a ripple, a big splash or whatever, and then as you move away from that splash, that point of contact, right, those ripples kind of die down, right? That'd be a so-called gradient potential, right? Variable strength, it could be a big boulder, it could be a pebble, right? But eventually, as it moves, as those waves move away from the point of contact, they're going to decrease in the amplitude. Okay? Whereas an action potential, we're going to see, is going to be more like the analogy of a string of dominoes, right? There's going to be a signal moving down, and they're all going to be exactly the same. They're not going to diminish in strength. Right? This is just the introduction. We're going to talk about these in detail here. Are you with me so far? Sure. Good. I like to hear that. So again, a graded potential. We talk about graded potentials here. A graded potential, that is the little ripple in the pond right here that's going to decrease. And that's going to happen. To that, there's a membrane potential to start with, and there's going to be some kind of stimulus or another. And that stimulus is going to open up some channels. Sodium is going to flow in, and in this case, we'll talk about depolarization. We'll put off hyperpolarization for right now. Just talk about this depolarization steps. That is, the change around the area of the cell, and here we'll always talk about usually the synaptic potential, what's happening in a synapse, but in any case, could be a receptor too. any kind of stimulus in the cell is gonna cause this wave of electrical activity, that is a flip in voltage, right? A temporary one that spreads throughout the cell, and like that pebble in a pond, right, is going to diminish as it goes from that point of contact. Yes?
So is it losing energy as it,
Well, we'll see
Travels?
how it happens, right? That would be a wave. In this case, it's gonna be losing a positive charge, a
Oh.
positive charge as we see, right? Don't get too much of the wave, that's just,
no, I know.
as far as the ripples go, that's an energy wave, right? That's moving up and down. In this case, over here, right, you got the stimulus, the point of contact in the middle right there, wherever that was, that causes a large depolarization, change in electric activity, right? It goes from -70 to say 50, right? -50, right? That's depolarizing, it's become less polarized at that point. The point of contact is strong enough, as it moves away in all distances, that's gonna kind of meter out right there. It's gonna flow out right there. It's gonna kind of calm down, right? Whatever it is, if it's a big one, it'll calm down it'll travel much farther. It's a very small one, it'll be very local. It's a local change in the particular membrane. Okay, that's a graded potential. That makes sense?
No.
No? Right, so maybe when we talked about, here, let me go to this next one here. Let me get back to this. Right. Maybe this will make more sense. Here on the top right there, number 1, where the green, well, those are ligand gated channels, right? This is what we'll talk about in the next lecture. At the synapse, right, there's gonna be a gated channel that opens up ion channels, right? So sodium channels, sodium's gonna flow in around that area of the dendrite. So you have another positive charges flowing around in that area right there, right? In the green areas where the synapse is. And then as that signal spreads, right, what happens over here, this was negative, negative charges are gonna move in, positive charges are gonna move out, they're gonna spread out, right? All those sodium ions are gonna flow out toward the general negativity of the cell. Any negative elements in the area are gonna flow toward that positive area. And as it moves away from the area, you got all those sodium, the potassium leak channels, potassium's leaving, the positively charged ions are leaving, and that's bringing that cell back to a more negative charge right there, as it moves away from the spot. That's what's actually happening here. So the potassium leak channels, right, are gonna be what is kind of bringing it back, right? First of all, it's a small place on the cell. This could really be, it's like exaggerating where it is. It's a small local spot into an entire cell. So that little positive charges is very local, negative charges move in, positive charges move out, and positive charges through the potassium ones are gonna leak out and make it more positive as it moves away. Okay? So it's gonna move down, and ultimately what we'll see is we want it to move, if we want to pass on that signal, we want to move on, it's gonna be kind of directed over to this area, but we'll get back to those voltage gated channels. So far, we just have a signal. We didn't really talk about that signal that started, but some kind of stimulus, right? It's gonna start it, and it's gonna be a local signal that has a sort of voltage flip from negative to positive, right? And then those ions are gonna flow around, potassium ions are gonna flow out. Yes?
So, the sodium channels open up first and then.
Yeah, so the stimulus could be different things, right? Mostly we'll be talking about synaptic, right? There's a release of a neurotransmitter that opens up sodium channels, that's the stimulus. But we could have been talking about sensory transduction too, but in any case, anytime sodium channels up, positive ions are gonna flow in, that's where sodium ions wanna go, they wanna go inside the cell. All those positive ions, all of a sudden, that's the electrical signal, that's the difference. So the cell, instead of being -70, all of a sudden -50, right, or -40, or -30, or all the way up to 0, right? That's the potential is being decreased, the potential difference, right? The difference is being decreased, that's a depolarization. And as you move away from that area of the initial stimulus, right, that polarization is gonna be less and less, and otherwise it's gonna be more, it's gonna go back to the polarization part, right? It's gonna go back to -70, away from there. Yeah.
Is there, well, it has to be a way for the sodium to stop eventually. It
Well,
can't
the
just-
sodium channels only open up for a second as long as the ligand ones are there. They'll open up and they'll be released and then they'll close. And this is just for the graded ones, right? All we're interested in right now is that there was a brief transitory influx of sodium ions. Right? And now that sodium ion stopped, but that electrical, those positive ions are still in there. They're gonna kind of diffuse, they're gonna be diffusing throughout the cell, but also sodium, potassium is gonna be leaking out. And that's gonna bring that back to resting membrane potential. All right, so if we look again over here, if it's a so-called sub-threshold, it doesn't mean, but like it's gone over, it's decreasing. If you measure it, right, you're gonna measure it over here, and you're gonna see it went from -70 to say -40 right there. And then if you measured it down here, it would only, you know, you measure the polarization, it would be -55 right here. And if you measured it way down over here very far, it would be below 55, right? So in other words, you see it diminishing, right, from the initial -40 to minus whatever, 255, and then below 55 right here. The number 55 would be key because the 55 is where maybe other things start happening, right? So if you get a very strong signal, very strong, there's a couple of different ways to get this. That signal, which started out above 40 or whatever, there's a couple of them, and it travels down and it reaches this point and it's above 55 still, that is, it hasn't diminished that much, right? That's where things start happening, right? So we've reached this trigger zone at a pretty high voltage because it was a strong stimulus of some sort, which we'll talk about tomorrow, how you get a strong stimulus. Okay, so we're almost done with graded potentials. And you're excited to see what's gonna happen next, I know. But that depolarization, there's a critical level called the threshold, definition, threshold, right? The critical temp is the level of depolarization. That's gonna activate the sodium, the voltage gated sodium channels for the most part, right? But in our situation. So the cell is gonna start, that passive spread is no longer the mechanism here. We're gonna have this active spread with these voltage gated sodium channels.
What was the definition of threshold again?
The threshold is the critical level where voltage gated channels open up, right? That's where the critical level. They're sensed, and we'll walk through this again as we talk about those sodium channels. But first, I know you're excited to move on here, but we're gonna go backwards here. Because remember, we talked about signal transduction in a receptor. Stimuli, light, chemical stimulus, and mechanical stimulus was touching on a receptor, and it opened up ion channels. In that case, if it was strong enough, it reached the threshold, calcium channels opened up, calcium flows in. That magically release causes the vesicle-filled neurotransmitter-filled vesicles to fuse the membrane and be released. And so going back when I talked about magical signal, threshold and depolarization, this is what we're talking about. The same thing we're gonna talk about today is relevant to all that sensory transduction stuff, right? The sensory sort of signals from a chemical or stimuli, whatever, into an electrical signal. All right? So that's from learning, that's from last lecture, but it's relevant today. And so if I asked you like something like this, a graded potential within a sensory receptor is, it's a receptor potential. It's just the same exact thing. It's a graded potential. All the same things are happening, except they call it a receptor potential. Then we get to synapses and stuff. We'll call it a postsynaptic synapse potential, right? But all these are graded signals that could be of various strengths, and they die out as they move along. They spread passively. Right? The cell repolarizes through those leak channels. You with me? Everybody's got a picture of that? If I put it here, it's not generally a test, but there might be something generally like it. These are ones I took off because they were similar to ones I had on there.
Just put it on the table.
Okay, I'll put it on there. It's already made. I made it test this time, so now I know what to emphasize. So, depolarizing, graded potential. Again, we want to start off, right, with signal, incoming signal, or whatever. Could be, if this could be anything. Doesn't really matter. There's a signal that's going to spread throughout the cell. It's going to die off or it doesn't, but if it's strong enough, right, it's going to be, this passive spread is going to reach, it's going to move toward the crucial axon hillock, right? which is the trigger zone. It's gonna sum up all the, there's gonna be, you know, we talk about one signal, but tomorrow we'll talk about a bunch of signals coming in. Some of them might be negative, right? But basically it's gonna sum it up. Is it strong enough? Does it reach threshold? Right? Where does it reach threshold, right? Is it strong enough, right? And then the last one will be, once it reaches there, now we're gonna start off with the next phase, right? The action potential, right? The more active one that's gonna run down the axon and eventually cause neurotransmitter release at the other end right there, right? So threshold is when the potential is strong enough, right? The difference. The axon hillock is the integrating center right there. That's gonna sum up the total of the signals that the cell is receiving. And then the action potential, right, is the signal is propagated down an axon in a so-called all or none, right? That doesn't lose strength, unlike the graded potential. The signal that starts right here is gonna be just as strong down here, every single branch off there, right? This is why we say all or none, but we'll get into that in a second. Everybody with me so far? Yes. So that trigger zone, and all those, at that point, it was moving passively, the signal was spreading passively, and getting weaker, but if it was strong enough, the threshold, these voltage gated channels in the trigger zone, right, were set off by that supra-threshold stimulus, that is above a certain voltage, and that caused it to open. Again, we'll walk through those exactly, but those are heavily concentrated around the trigger zone. Right? Once it starts there, in the trigger zone, then we start the action potential, right? But the voltage gated channels are where the cell is actively responding, right? It's no longer a graded potential, no longer passive spread. Right? So here, anybody know what that is? It's a
It's a dead pit.
eel. Anybody know what this is?
Blowfish.
Anybody ever eat these?
No.
People eat these, you know, but they don't eat them like that. So what happens? This fish, this moray eel tried to eat this, a little fish, and the fish blew up. And it wasn't like the spikes that killed that fish. I just want to tell you that they found this on the beach last year. I just want to show you. It doesn't have anything to do with the lecture. Just want to take a break. This is in LA. No, I'm just kidding. Right? The pufferfish blows up, but that's not the interesting part about the pufferfish for us. The pufferfish has bacteria that live in it that produce this toxin right here, tetrodotoxin right there. It's a chemical that it produces, and that's why the eel died. The eel died because this tetrodotoxin, what did it do? Tetrodotoxin flows around the body, gets in the extracellular fluid. It goes anywhere where there's excitable tissue, like your heart, like your breathing muscles, anything like that, and it blocks those voltage-gated sodium channels. When it blocks those voltage-gated sodium channels, there's no electrical activity, there's no action potentials. All your muscle cells are excitable like this, they're gonna use the same mechanism. Your heart muscle cells are excitable, they're gonna use this mechanism. If you block that channel, it's you. Dead fit. Basically, your heart stops beating, right? You're paralyzed, right? And you end up. And also, like local anesthetics, they can work that way, but they're local, right? They're not going to spread throughout your entire heart and your breathing muscles. You can block signals like pain and stuff coming through by blocking these channels. Right? You're not going to use that kind of toxin, but in any case, this is just to show you voltage-gated channels. They're the key to the cell's excitability. So let's walk through it. Over here, resting membrane potential. Over here, and we're sitting there, their sodium is kept out because of the phospholipid bilayer. It would like to get in, but it can't. Right there. At a certain voltage, over here, at minus 70, those gates are closed. Sodium cannot get in. Right? Upon the depolarizing stimulus, threshold stimulus, those voltage-gated channels, these little voltage centers, right, inside right here, here that open up. It opens up a little gate, and all of a sudden, this sodium selective channel allows sodium to flow in toward down their electrochemical gradient. It's attracted to the negative charge. It's attracted to the lower concentration of sodium. Mostly, it's the electrical charge, very highly negative part right here. Right? So as it flows in, over here, what happens? What happens to the inside of the cell? Well, over here, it's going from minus 70, and the potential is rising right here, right?
If you have
Becomes more
because it's
positive.
depolarizing.
Right, so activation gates are now open. They're flowing in the inside right here. The outside, the local area right here is getting more positive, right? And that's what you're seeing over here by this graph right here. It's going from -70, right, at time 1, right? You measure it at time 2. It was raised a little bit. That's probably where the depolarization stimulus happened. Right? And then you measure it at time 3, and all of a sudden we're getting close to 0. That is, it's being totally depolarized because all the sodium bringing in that positive charge is depolarizing it. Okay? So it was activated because those are gated channels. They're voltage gated. The change, that stimulus reached the threshold. When they get -55, they open and more sodium is flowing in. That makes sense? That's what's going on right here. Here's the other thing. We didn't talk about this. There's another gate. It's called the inactivation gate. Okay, but we're not going to talk about that. But no, this is going to be a different thing, right? But right now, let's just focus on the fact that this activation gate opened right here. Ignore that other gate for a second. So, action potentials. Once that starts, it's going to travel down the axon in a so-called all or none. That's the typical description. All means that if it's going to occur, it's going to occur, and it's always going to reach about +30 every single time. It's not going to be a stronger stimulus won't make it be +40 or +50. A weaker one won't make it +20. It'll always be +30 millivolts, right? The voltage, the amplitude is always going to be the same, and it's going to be the same all the way down the line. It's going to reach, if it branches off 50 times, each branch is going to have the same exact action potential going down. That's what it means, all or none. So if it doesn't reach threshold, it doesn't fire. It could be -54, and it doesn't fire. If it's 56, it fires just as strong as whatever the, -60 or whatever, right? Or -30 or whatever, it doesn't matter. If it reaches 55, that's enough to send an all or none signal. You understand the difference here between the, oh, you're happy sound. Right? Now you see the difference now between the graded, right? This is an active one, it doesn't change, it's gonna travel, it could travel from your spinal cord all the way down to your big toe, right? That could be, a foot or 2, whatever, 3 feet, all the way down, and it's gonna be just as strong when it started as when it ends. Right? Unlike your graded potential, right, which is gonna wear out, it's gonna phase out as it moves away. Right? So we get that thing, all or none, what that means, right? What does the signal all or none mean? Question number 24. Right? Something like that. It means that it doesn't go down, right? Constant amplitude. Okay, so what's happening, and don't worry about if you don't understand exactly what's happening. I'm not gonna, I don't know how to ask the question about this, but basically, when that positive charge goes through, right, it's gonna move in right here, and that's gonna make the cell inside more positive or more positive relative to the outside, but those positive cells, this is what happens basically any kind of potential, right? They're gonna move toward the negative part, the negative parts are gonna move toward the positive part and vice versa, right? They're all gonna kind of move each other. And as the signal moves down here, as the positive ones move toward the negative, this end up over here is gonna get more positive, and so on as it moves down there. Again, you could work it out if you want to, but the signal is gonna be traveling down the axon in a way like this. One section opening up the next section due to this depolarization, opening up sodium channels, voltage gated sodium channels all along the way. Okay? So when you look at a graph, again, here, that little measurement thing, you're taking measurements as a point of time. You take it here, it's -70. You take it here, it's -70. You take it over here, this is time. And you take it over here, all of a sudden you notice it's -60 or whatever, -55. Then you take it over here, like 1/0.1 of a millisecond later, and all of a sudden, holy, it's -10. You take it over here, and it's +30. That's what this chart means. It's looking at the change in potential in a particular area, right, of the axon, and this is what's happening, right? Basically, right? The action potential, the sodium is moving in, making it more positive, right? At a certain point, it stops, it peaks. It happens to peak around +30, which happens to be the equilibrium potential of sodium, right? The sodium will keep flowing in, basically, until it reaches +30. That's where its concentration and electro gradient has been sort of equilibrized, but that's where it stops. And then all of a sudden, it's being repolarized, right? You take it over here, and all of a sudden you're like, oh, so if you took it over here and here, you might miss this whole peak, right? You might miss this point, but if you take it at short enough sections, you'll see this whole curve right here. Everybody kind of understands what this curve means, right? I could put this up here, this curve on the exam right here, and maybe RB, if you want to leave it up here just to kind of understand it, but you should be able to interpret whatever's happening right here, right? And then to add to this, we're going to talk about what's the ion flow at any particular point in the curve right here, okay? So all this is a change. We're recording the voltage over time, and we're seeing how it changes, and we're going to see how it changes as a matter of influx of sodium, outflux of potassium, or anything like that. Okay? So you thought this is so complicated, now it seems pretty easy, doesn't it?
Yeah.
Right? Alright, so it goes down. You have a whole bunch of sodium ions in there, but you know, that wouldn't be enough to bring it back down right here, right? So why is it repolarizing so fast, right? And this is all milliseconds, right? This is all happening in, because remember, when we did the reflex thing, you tap your toe, that signal goes up to your spinal cord, right? The sensory signal goes all the way back down, right? That's super, super fast. This is milliseconds here that this is happening in any particular section. Right? So why is it going back down? Right? Why is it repolarizing? In fact, why does it go so far down that it's going to go below resting memory potential?
Because of the potassium leaking.
Because of the potassium channels. Here's a description. Again, you can kind of, if you want to figure this out, we'll just look at this other channel right here, but basically voltage gated channels open up, voltage gated sodium channels are opening up, positive flow in this area, right? Positive flow in the next region, right? I mean, all this positive is going to go to the next region, depolarize this region, right? And then behind it, we'll see that everything's going to stop, right? The signal is going to be spreading down one way, right? It's going to be spreading down in one direction. Why isn't it going backwards? And why is it repolarizing is the next question. So, remember I said those inactivation, that second gate in the voltage gated sodium channels, there was a second gate, a separate one. This is more like a time thing. Pretty much very quickly after these open and sodium flows in, this other gate, that's just like, you know, you press open a door and it closes automatically, it's gonna stop, right? And even if this is open, right here, sodium is gonna stop flowing in. Right here, right? And so you notice over here, right, this closes over here. This was around the peak over here. So note, at this point, this is where sodium stops flowing in, right there, okay? So sodium was flowing in, and now that inactivation gate, which was just a time gate, didn't have anything to do with a particular voltage, right? It just stops it and plugs it up. Sodium stops going in, right? And then at a certain point, both of those will be back open again, right? But for a little while there, it's closed and no more sodium could come in, right? Stopping the sodium influx, okay? So when we look at a chart like this, there's a superimposition of the voltage, right? The ion, the voltage on one side, right? And the ion permeability that is over here, right? They're looking at, this is ion permeability. Very permeable, like lowly permeable to ion, right? During the rising phase, it gets more and more permeable, right? The sodium, right here, becomes more and more permeable, and then at some point, it becomes less and less permeable. At the same time, right around the same time, these voltage-gated sodium channels, voltage-gated potassium channels are opening. This is where it gets confusing. This is physiology. There's several things happening at once. This is where you gotta take things one at a time. But these gates, the key here is they're very slow. They're slow to open. So sodium, potassium efflux going out of the cell isn't that great. So it doesn't contribute, but over time, right, it does start to contribute, and that contributes to this falling phase. Right over here, that is the opening of the potassium channel, which does what? Sodium, potassium is gonna flow out along its concentration gradient. That's making the cell more negative. In this case, it's repolarizing. Okay? Think about this, you have to work it out a little bit, just, it does work out, right? That the timing of the sodium, the potassium channels opening up is gonna start the repolarization. And the fact that those potassium channels close very slow also, that is, they remain open longer, is why we're gonna get this next phase over here, right? We get this after hyperpolarization phase. Okay, that is, the potassium flows out so much that the cell becomes less negative, and more negative, sorry, than the -70, it gets to about -90, which is the potassium equilibrium potential, right? That's where it'll go till where it stops right there. Okay, so you got this immediate depolarization, a repolarization, now you got a hyperpolarization. Right? And that's due to that slow potassium channels, positive ions flowing out, making the cell more negative. Right? And then the last phase is, right? The last phase is, right, this resting phase, everything's turned back to normal, right? Those voltage gated potassium channels, which was allowing this potassium to flow out, they're gonna close. And then that whole sodium, potassium, ATP pump, all the leak channels, bringing everything back into the resting phase. Okay, and then this chart over here, this is a big one. This is kind of has everything in it right here. On this side, you got ion permeability, that's showing sodium and potassium inflow and outflow right here, right? In this case, this rise over here means the permeability is increasing, but there's an outflow of potassium. This wave over here is the sodium influx, right? And then this is the actual voltage change in red, right over here. Does that make sense how this chart is? Telling you how to understand this. This gives you all the information you need to know about everything that's going on in these channels right here. Right? So we look at the corresponding sodium channels open over here with the activation gate, right? That'll be all about the rise over here. Right? We're at the same time the slow potassium ones, right? These sodium ones close, potassium opens. Right? And this is a rise. This is the permeability change, but potassium's flowing out, and you're repolarizing the cell, right? Going down. Right? And then at the end, right? And again, the potassium flows out enough so that there's actually a negative charge. Right? And then the fact that it's these two combinations, right? The sodium inactivation gates, right? They're not going to allow any sodium in, no matter what the stimulus is. That's called the absolute refractory period. During that time, that is, you can stimulate it all you want, and because those inactivation gates are still closed, you're not going to be able to stimulate. So there's a time limit on how many action potentials you can have. After that point, after those inactivation gates are no longer closed, right? At that point, you're still going to be hyperpolarized, right? That's called the relative refractory period, where it's going to be harder to stimulate the cell, right? You need a stronger stimulus at that point. Right? Those are refractory periods, absolute and relative. Okay? So, when I talk about that, the excess potassium out there, hyperkalemia is potassium, right? The hyperkalemia, too much sodium, and if you have too much sodium in your blood, your extracellular fluid, right there, that's going to actually bring, because it's going to become more positive, right? It's going to bring the cell closer to the threshold, easier to stimulate, which is bad. We want it just at minus. We want everything normal, right? That's the normal operation. You're trigger happy at this point because your cell is less polarized to begin with. Whereas hypokalemia, is going to do the opposite. You're going to be harder to stimulate, right? So these are dangers why potassium balance in your body is so important, right? The excitability of the cell is going to be very changed right there, okay? And there's other factors that affect those channels and stuff, right, that are going to be a major factor in all these. Keeping, right, precise amount of the electric balance right there, proper. All right, one last thing. One last thing, there's an electrical signal, that depot, that voltage flip going down an axon, right, is happening like this, right? If you insulate the axon, and we're not gonna really get too much into detail, luckily. There's these myelination, there's these insulation strips, right, done by glial cells, right, that are gonna insulate the axon, with the exception of a couple of so-called nodes, spaces in between. And the signal is going to jump from signal to signal and make the signal incredibly faster, like 70 times faster or something like that, right? Maybe 7. It's a lot faster. I'm not gonna ask you how much, but it's a lot faster because it's going from node to node instead of going down step by step. Right? And so, again, just to kind of tie this back to, you know, your organization of your nervous system, white matter, and your brain, those are all myelinated axons. That's bringing things from one region, right, of the brain to another, right? Going from this side of the brain to this side of the brain, from this part of the brain to this. This is all myelinated axons, bringing very fast signals over here, or your nerves are all myelinated axons also, right? So this is all very long distance, very fast signals, cables bringing information from one place to another. Right? And again, I'm not gonna ask you this either, but don't worry, right, how the actual ones work, how it goes from node to node. But you could think, I think somebody put an analogy right here. Right? If you put your space bar, right, you tap one at a time, you hold it down, there's a signal going down like put a letter down your typewriter page, versus putting the tab bar, right, which will be much faster right there. Right? So basically the signal is moving much faster than it would with these myelin sheets. That's one way we can make the signal move faster. But here's the last thing. The other way you can make the signal move faster is, this is all about understanding how electricity flows and resistance and stuff, right? The bigger the axon, right? The wider the axon, the more surface area right there, the faster the flow, right? This is something we'll see with blood flow too. All axon stuff has been studied in the so-called giant squid axon. It's like this big, you know, it's like a millimeter or something. It's not that big, but they use it to study. It's not myelinated, but it's very fast because it's big, right? There's very little resistance in a large axon. Right? So you can do two things for an axon. You can make it bigger and you make it myelinated. A big myelinated axon is going to be much faster than a small unmyelinated axon. Okay, those are two things that affect the speed of the axon moving down the axon. Okay. Okay. Does a larger axon increase? Now this word, you can learn it, but if you see the word resistance, that means resistance. That's going to make things slow down, right? So a larger axon, myelation, right? That's going to decrease resistance, make the speed go faster. This will be important for blood flow too, right? So also, when we talk about the pathways, going from over here, we talk about that gate theory here, right here, where the touch fiber had these big so-called alpha beta fibers, large myelinated axons going in, whereas the pain fibers were small, unmyelinated axons, are much slower. And that's why your rubbing and everything is going to be a lot more faster and kind of be able to tamp down that signal. And that's just an example from last time. Okay, oh no, here's one last thing. It's related, right? Over here. Demyelination diseases, right? Multiple sclerosis, other ones over there. What they do basically is they chew up, there's your own body, your own antibodies, your own immune system is chewing up those myelin sheets. Right, that causes a signal delay, right? Anywhere we're moving, whether it's peripheral or central, right? All those diseases are demyelinating diseases, affect the speed of transduction, right? This is why they cause all these motor and sensory symptoms right there, right? Also, by the way, probably caused by a virus infection at some point in your life. So, that's just speed. I think that's it.
Rested now.
Oh, which of the ones should I
Right, those are the differences. You know, A, B, and D are the differences, right? Between them, both of them though are going to be about ions moving across. That's the whole thing about change in permeability, right? All right, see you for tomorrow. Again,